Welcome to E105 discussion 13. So in this discussion, I'm going to talk about the MOSFET analysis. You will see some MOSFET problems in homework 11. And Professor will cover BJTs in the lecture, so we will do MOSFET here. And also I will give you some hints about homework 11 problem 5, which is kind of hard, the last problem in the homework. I'll give you some hints. And we will just discuss some differential pairs. I think Kieran has discussed this in last discussion, but I'll just do some recap here. So first, I will just give you one example of MOSFETs. So this is a simple single transistor circuit. It just has a MOS M1 here. And all the parameters are given. And I want you to find what's the value of RS2 that could make this circuit has a current IC equals to 100 microamps, and also what's the input resistance Ri. So the Ri is a small signal input resistance. I also want to find an expression for FH, basically use OCTC for the circuit and find the FH. And all the CG, CS, so all of this are bypass capacitors, so their values are large enough. You do not need to consider them in the FH analysis. So this is just the problem. It's quite easy to read, so I'll just start. First, find RS2 that makes IC equals to 100 microamps. So the thing is, the MOSFET is different. It's kind of different than what we have seen before because it has the body connected to the cells. So yeah, the default, what you have seen before, we don't have the body wire. So we just, the default is your body is connected to the source. But if there is a VSB in between, so there's a voltage difference between your buck and your cells, then your VTN, your threshold voltage will not equals to VTN 0. So there is another expression for threshold voltage if you have a VSB not equals to 0. However, in this case, your the B terminal, the buck terminal is connected to your cells. That means your VSB equals to 0. We can just say VTN equals to VTN not, which is 0.7 volts. So the turn-on voltage for this transistor in the circuit is just 0.7 volts. You don't need to consider you don't need to care about the 2 phi f. This is related. This is used when VSB not equals to 0. So just ignore it. It's pretty simple right now. And then let's go back to the problem, how to find IC equals to 100 microamps. The current equation for the MOSFET is ID equals to mu n C ox W over 2L. So the first thing you have to assume is your MOSFET is in saturation regime. So always assume M1 in saturation regime. The saturation regime is what we usually use for MOSFET. Just like you have to assume the BJT is in forward active regime. That's just the convention. So the current equation for saturation MOSFET is mu n C ox W over 2L VGS minus VTN squared. We also have 1 plus lambda VDS, but as you can see here, the lambda is small, so you can just think this is small. You can just ignore it, which the ID equals to 100 microamps. And we have mu n C ox is 200 microamps per volt squared. And we also have 100 over 1, so this is W over L. If you say like a ratio right next to the MOSFET, that means that's the ratio of your W and L. So that's the ratio of your width and length. So all the things are fine here. You can just calculate what's your VGS. So your VGS will be 2ID over Kn. Well, Kn is mu n C ox W over L square root plus VTN. If you do the calculation, plug in numbers, you get VGS equals to 0.8 volts. So in order to have an IC equals to 100 microamps, your VGS must be 0.8 volts. Then let's say what the value RS2 it should be. So the value RS2 should equals to Vs divided by ID, the current. And your VIs, the voltage at the source, will equal to the voltage at the gate, so the VG minus VGS. And what's your VG? Your VG is the current I bias times R1 plus R2. So our VG equals to I bias times R1 plus R2. And I bias is given here, is just as a constant current source. So just plug in numbers, you'll find RS2 equals to 7 kilo ohms. So this is just the DC biasing of the MOSFET of the circuit, so it's quite simple. We have found our RS2. And then find Ri of this circuit. So Ri is here. This is the small signal resistance. You have to do the small signal analysis of this. So here I'll use two methods to solve Ri. So the first method is just a regular one. So we'll do hybrid pi. So hybrid pi means we just redraw the circuit into the small signal model, replace your MOSFET with the hybrid pi model. So the small signal circuit will just be Vs, which is an AC signal, Rs, and all the capacitors, are short circuit in AC, in small signal analysis. You can just short them. And so your small signal circuit would just be Rs, R1, and GMVGS. We have our RO. And then connected to your R2 in parallel with RS2, another RD1 plus RD2. And this is your V out. This is your gain. This is your, okay, so your V out is actually not here. This is your V out. And you have RD2 and RD1 here. So this is the actual small signal model of your circuit. The thing is, so in the before you have seen a common source model that your source of the MOSFET is directly connected to the ground, but here is not. So your source is connected to two resistors in parallel with each other. So R2 and RS2 are in parallel. And this is your source. So your source is not connected to ground anymore, and you have a drain here. So to find the input resistance, that means you have to, the input resistance is right here. So it's let's just use let's just find the input resistance of the whole circuit. So let's do here as your Ri to make it easier. So your Ri would just be the resistance to the left of your current source. So to find Ri, what you have usually do is we just give it a test voltage and find what's the current of it. Then your Ri would be Vx divided by Ix. So basically, is equals to Vs divided by Ix. So we just need to know what's the current that flows through the Vs or voltage source, and then take the ratio, we'll find Ri. So the key point is how to find your current. So to find the current, basically we always do KCL or KVL for the circuit. So let's do a simple KVL in this loop. So from VS to the ground. And as you can see here, what's the RO? The RO is definition is lambda ID inverse. If you plug in numbers, this is really large. So ID is like 100 microamps, and your lambda is 0.01. If you plug in numbers, this is really large. That means we usually just ignore R naught. So we'll just treat R naught as an open circuit, just to simplify our equation or process. So just let's do a KVL for this loop. We will have Vs minus Ix times Rs minus Ix times R1, and then minus R2. Yeah, let's see R2 in parallel is Rs2 equals to Rs or capital S. So I will just use this symbol to represent the two resistors in parallel with each other. So it will just be R2 times, it will just be R capital S, the two resistors in parallels, times your Ix plus Gm VGS. The current that flowing through the R capital S equals to the Ix and also this voltage controlled current source, if we ignore R naught. So R naught is large. And then to the ground equals to 0. And another equation we have to know is we have not defined VGS here. And VGS is the voltage between your gate and your source. Is the voltage across R1. So the voltage across R1 here will just be Ix times R1. That's VGS. So just use these two equations, plug in numbers, you'll find Vs equals to Ix times Rs plus R1 plus R capital S1 plus Gm times R1. So your input resistance here is Rs, R small s, that's the resistance of your voltage source, plus R1 plus R capital S, which is R2 in parallel with Rs2, 1 plus Gm R1. So this is solved. This is the first method to solve this input resistance. You can use it. You can always use it. This is always true. But it's kind of tedious. You have to do a small signal analysis. You have to redraw the circuit, write KVL. The next, a much easier method I'm going to say here. So let's do method 2. It's like inspection analysis. So if you recall the inspection analysis we have done for BJT, so you have a BJT here. This is NPN, right? This is your base, this is your collector, this is your emitter, and you have a RE here. This is the emitter. And this is the collector. Okay. And the inspection analysis we have seen is they are in or RB. So the resistance looking into the base equals to R pi plus beta plus 1 times RE. So let's say BJT has a resistance to R pi. So the base is connected to R pi. Well, for the MOSFET here, so let's recall. The small signal model for this is R pi plus minus VBE, and then a GM, and then an RO connected to RE. This is the small signal model for the BJT. And for the MOSFET in the left, we have R1 plus minus VGS. And we have a GM VGS. We have an R0, and we connect it to the R capital S. So those two are almost the same. They just have some like values are different, but almost the same. So you can just treat them as the same. They have the same relationship between each parameters. So if our BJT has R pi and our MOSFET has R1, those two are just symmetric. So R pi and R1. And the BJT has a small signal input resistance as, let's do this. The BJT has a beta, right? Has a beta. We'll do step by step. The beta of the BJT equals to GM times R pi. So you have you call your R pi is beta over GM. So your beta equals to GM times R pi. Then your beta for your MOSFET, let's call beta effective. The effective R beta of your MOSFET, just plug in, replace R pi by R1, will just be GM times R1. Then what's the input resistance for your BJT? And by inspection analysis, we have defined this. So your input resistance is R pi plus beta plus 1 times RE. And the RE here is the resistance at the emitter of BJT, which equals to the R capital S for MOSFET. So just plug in numbers. The input resistance of your MOSFET will just be R1, which is R pi, plus beta effective plus 1, which GM R1 plus 1 times RE, which is R capital S. And here the only difference is we forgot the source resistance RS, so just plug RS, and we got it. So this is a much easier method, a much easier way to solve for input resistance. Just basically just by comparison, our circuit with the BJT model we have learned before, but they will give you the same answer as hybrid pi analysis. Just FYI of this, you can choose whichever one you want to use, but both are correct. Okay, so this is how we find the input resistance of the MOSFETs of the circuit. Next one is to find FH, so the high resistance of your circuit. So FH, we always do open circuit time constant analysis. That means you'll have to open the other capacitors for each analysis of your time constant. The main difference between BJT and MOSFET is kind of same. Yeah, right. Your C pi, so BJT has C pi, while MOSFET has CGS, and BJT has C mu. Your MOSFET has CGD. The only difference is your MOSFET also have CDB, which is the capacitance between your drain to the buck. So this is one more capacitors you have to care about. So let's draw these three capacitors in the circuit. So CGS is the capacitance between gate and source. CGD is the capacitance between your gate and drain. And CDB is the capacitance between your drain and your buck. So this is B, this is G, this is D, this is S. So we have three really small capacitors we have to care about for the FH analysis. So yeah, we have not defined the GM for the circuit. So the GM for MOSFET is 2ID over VOV, with your VOV equals to VGS minus VTN. The VGS we calculated in previous slides is 0.8 volts, and your VTN is 0.7 volts. Your ID is 100 microamps. So just plug in numbers, you'll find the value of your GM. So GM is 2ID over VOV. It could also be many other another notation for GM is mu n C ox W over L VGS minus VTN. So there's several ways to calculate GM. Let's do small signal analysis. Let's draw the small signal model of that's the whole circuit. So include CGS, CGD, CDB in the one circuit. So the small signal model will just be this AC sources, and you have R1 connected between your gate and source. I'll just ignore the R0 because it's large. R capital S. I'll just use RD to represent RD1 plus RD2. So that's the small signal for the circuits without capacitors. Now let's add the capacitors. So you have a CGS between G and S, the gate and source. You have CGD between gate and drain. And you have CDB. But the thing is your buck is connected to the cells. So CDB will just be drain to the cells here. So you have 3 resistors like this, 3 capacitors included in the circuit. So this is the whole small signal circuit of this problem. So to do OCTC analysis, that means you have to find your FH equals to 1 over 2 pi summation of tau. To do you have to find each tau for each capacitors using OCTC analysis. So you have to let's do OCTC analysis for CGS first. So let's do CGS first. Let's define the tau GS equals to CGS times RGS. We have to find what's the RGS. So the whole circuit will just become this. So let's recall what's the OCTC analysis we mean here. So OCTC, that means we have to open the capacitors not used. So right now we want to do CGS. That means you have to open CGD and also CDB. Another thing is to replace your capacitor under analysis with a test voltage Vx. And you have to find the Ix through it, then your RGS will equals to Vx divided by X. So the same OCTC analysis as you have done in BJT. So to solve this, we have to do KVL again. So always KVL or KCL. I'll write 2 KCL in this case. The first KCL, I'll do KCL at the gate terminal, and then I'll do another KCL at the source terminal. So at the gate, your KCL becomes, I have my VG. So that is a gate voltage, VG. Yes, and don't forget to short all the other voltage sources. The first is your VG is VG divided by RS. That's the first current flows out of your G. And the second one is VGS divided by R1, will equals to the current flows in is IX. So this is the first KCL. And my second KCL is for the south terminal, so S. So S will be, I have my VS as a voltage as a source divided by R capital S plus Ix. So those two are flows out of the source. Those two should equals to VGS over R1 plus GM times VGS. So just using those two, you can solve for Vx and Ix. So first you have to, for this one, you have to find, you have to represent, yeah, so, and another thing is, yes, I have to include one more here, is my VGS equals to Vx. VGS is the voltage across R1, which is just Vx. So just using these three, you have three equations and two variables. It's easy to solve. Just by solve this, it will take some time, but it will give you some the answer. So just by solve this, you will get your RGS equals to Vx divided by Ix is, it's quite long, R1 R small s plus R1 R capital S over R1 plus R small s plus R capital S plus GM R1 R capital S. So this is your RGS. It was kind of long, but if you just do the KCL and solve it step by step, you will get the answer. So the first time constant is done. It's just CGS times the RGS we calculated. And the another capacitor we have to care about is CGD. So we have to do same analysis for CGD. So we have to care about these capacitors. But so for now, let's use instead of just keep it as a shunt capacitance, basically a capacitor that connects between your gate and drain, we can use Miller effect to simplify our analysis. So for Miller effect, let's recall this. If you have a op-amp and you have a C here, and the op-amp has a gain A, so A is the gain of your op-amp. This circuit will, these capacitors will be equivalent to, this circuit will be equivalent to a C1 and a C2 at both input and output, with C1 being 1 minus AC, and C2 is 1 minus 1 over AC. So that's the Miller effect. So it will convert one shunt capacitors into two capacitors at both sides. So CGD here can be converted into, let's say CGD1 and also CGD2 to the ground. So we want to simplify, make it easier to analysis. Then your CGD1 equals to 1 minus A times CGD. And the A is the gain between gate and drain of your MOSFETs. And if we recall the inspection analysis we have done for MOSFET, the A is gate to the drain is negative capital GM times R naught. And your capital GM is GM divided by 1 plus GM R capital S. And your R naught is RO plus GM RO R capital S, and parallel with RD. Just the inspection analysis. Just plug in numbers. The thing is, your R naught plus GM R naught RS is large. So there's a large value in parallel with RD, which just give your RD. So the actual gain of your circuit used here would just be negative GM RD over 1 plus GM RS. That's your gain. So your CGD1 is 1 plus GM RD over 1 plus GM R capital S times CGD. Similarly, your CGD2 is 1 minus 1 over A. But since your A, if you calculate this, your gain is large. This is a large value. The actual gain is large. So if you take the inverse, it will be small. So this is small. So in other words, your CGD2 will just equals to CGD. So this is by doing this, we convert our CGD into two capacitors, one at input, one at output. Then your let's do the time constant analysis then. So the time constant analysis, I'll define my let's draw. Still keep them here. This is CGD1 and CGD2, and don't forget you have another CDB connected here. CDB. Okay, so let's do the first one, tau g, which is the time constant for CGD1. So the tau g will equals to RG times CGD1. And what's the equivalent resistance seen by CGD1? So the first thing you have to know is there's no current that could flows into the gate of a MOSFET because it is insulated by an oxide. So the resistance at this direction is infinity. So the resistor seen by CGD1 is actually on the other side, so it's to the left. I'll not explain it in this way. It will be hard to understand. Let's just say, what's the resistance seen by CGD1? So the resistance seen by CGD1, the RG, will just be, you have to remember we have calculated the input resistance before. So we have an Rin here, right? The Rin is, we have calculated Rin in previous part. And we also have an RS. So that the resistor seen by CGD would just be something like Rin and RS and another CGD. This will be the circuit or equivalent circuit of the CGD1, what CGD1 has in here. So the RG or the equivalent resistance seen by our CGD1 would just be Rin in parallel to RS. I just see it here. Actually, you can do a tedious analysis, basically using OCTC analysis again for CGD1 and to find the resistance. But if you do that analysis, you'll get the same result. So the RG would just be RS in parallel to Rin, and Rin is what you calculate before. So just plug in numbers. We got tau g, and your tau. The other one is, let's define it as tau d. This is the time constant for CGD2 and CDB. So your CDB will just, so the tau d will just be C, so the CDB and CGD2 are in parallel, so it'll just be CGD2 in parallel, that means plus CD, that's CDB, that's your capacitance. And you have to find what's the RD, what's the equivalent resistance seen by those two capacitors. Well, this is, I'll just draw it here. So you have a capacitor here, that's, let's call it C. And the resistor seen by those two will just be, it will have a RD on the top to the ground. And it also has R capital O to the ground. That's the equivalent resistance seen by the capacitor. Well, the R naught is RO plus GM R naught R capital S. So the RD is R R small d is R capital D in parallel with R naught plus GM R naught RS. So you have to recall this. This is by inspection analysis. This is equivalent resistance seen downward of your drain. So this is R naught. And your R naught is large. Our R capital S is also large. So if you take the RD in parallel with this large resistors, you will get just RD. So your R small d equals to R capital D, which is RD1 plus RD2. So basically everything is solved. Just plug in your values to get the tau D, plug in values get tau G, and plug in values to get what we had found before, the tau GS. So the final answer would just be, your FH will just be 1 over 2 pi times the summation of taus, which is tau GS plus tau G plus tau D. And that's it. That's the FH of this circuit. Just plug in numbers and you'll get the answer. Okay, so that's the inspection analysis we for the MOSFET we'll cover here. We'll just basically give you an idea of how to solve MOSFET, how to solve CGD, CGS, how to find the FH. And this move on to next part is I'll just give you a hint of the problem 5 in homework 11, which is due next or this Friday. So for this one, one question asked in problem 5 is to find the gain of the whole circuit. So I want you to find what's the V out over VI, but this is like kind of hard to analysis. And the hint I'm going to give you today is how to solve the first stage gain. So you can see this is a 3-stage circuit. This is the first stage. So it's number 1 stage. And this is the second stage. So the first stage will give you a gain. And the second stage will give you another gain. And this is the third stage will give you a third gain. And the final gain will just be the gain of the first stage times the gain of the second stage times the gain of the third stage. It's just a product. But the first, how to find the gain of the first stage is the most difficult one. So I'm going to tell you here how to solve it, how to find the gain of the first stage. So let's do it step by step. So first, I'll just draw the hybrid pi model of the MOSFET. So what you have seen before is you have a your gate VGS, you have a GM VGS, you have R naught, and this is to the S. This is a hybrid pi model we usually use for MOSFET. And if you recall what you have learned in BGT, so for BGT itself, it has a hybrid pi model. It also has a T model. So BJT has hybrid pi and also T model. Actually, MOSFET also have pi model and T model. To solve the first stage here, to solve the gain of the first stage, it will be much easier to solve it using T model. So the T model for MOSFET is, it looks like this. So this is your drain. You also have a gate, and you also have an S. But you will have an ID here and a resistor connected between your gate and source, which is 1 over GM. So this is a T model for a MOSFET. I would say these two are equivalent. So both are correct models for a MOSFET, but we will choose to use T model here to solve the first stage. I'll explain it here, like how we do it. So first, plug in the T model into the circuit. So basically replace the two MOSFETs with the T model and draw the small signal circuit. So small signal circuit First, you have to short your voltage source, so VDD to the ground, and then you have to open all the current source. So I1, I2, I3 are all open. So just open it. Then your first stage becomes ground to the RD, another ground to RD. Now this is your drain, and this is your drain of M2. Replace the MOSFET by T model. So you have ID, ID. This is your gate of M2. This is your gate of M1. And you have 1 over GM, 1 over GM. And here is your sources of 2 MOSFETs. But the thing is, the source of those 2 are connected to each other, so just connected. So this is the equivalent circuit, a small signal circuit of your first stage. It's quite simple. And don't forget, we have a VI here. Oh, it's not ground. We have a VI here. Well, the other is ground. And then we want to solve the output is at the drain. So we want to find what's the V out over, let's say V out 1 over V in. We want to find the first stage gain. This is AV1. So how to solve this? The first thing is your gate have a VI, and the other gate has ground 0. So there is a voltage difference between 2 resistors. In other words, there must be a current that flows through these 2 resistors, 1 over GM. So what's the current? Let's call it I. Let's call this I. So what's the I? The I will just be, the voltage difference is VI minus 0 divided by the resistor is 1 over GM in series with 1 over GM. So it's 2 GM VI. That's the current that flows through the gate and source. I mean, that flowing in this direction. But the thing is, for MOSFET, your ID is usually equals to IS. That means the 2 current source here will have the same value as I. So ID will just equals to I. This is a voltage controlled current source, but you just need to remember the value of your ID equals to the current that flows in the source. So it just equals to I, which is GM VI over 2. So recall, you have ID equals to I here. But the thing is, let's see this part. This is your I, and your ID equals to I. So it will be same in this direction. So your ID equals to I. So I will just flows up. What's your V out? Your V out 1 will just be I times RD, right? So the V out is a current that flows through the RD times RD itself. And your I is it current? Oh yes, it's positive. So it's just I times RD. And your I is GMVI divided by 2 times RD. So it's GM/RD divided by 2 times VI. That's your VL1. So what's the first stage gain? The first stage gain is VL1 over VI is GM/RD over 2. So it's solved. The first stage gain is GM/RD over 2 divided by 2. And it's solved. So the key point for this problem is replace your MOSFET by T model and remember ID equals to I. which is GM divided by 2 times VI. So that's how we solve this. And another hint, because this problem also asked for input resistance. So to solve input resistance, you always need to use Vx divided by X. So you always need to give the input of Vx, a Thys voltage, and then you have to find what's the current that flows through the Vx. If it has a current, then you will have a finite value. But if there's no current flows through the voltage source itself, it will just be infinity. But you have to find it by yourself. And actually, if you listen to last week's discussion, this is the same as a diff pairs. So I'll just draw the diff pairs here. So this is what a diff pair looks like. I'll just briefly draw it since we have no time left. VO1, VO2. This is a diff pairs. What's how a diff pair looks like, and this is just similar to our P5 problem 5. But the only difference is for diff pairs you have VI1, VI2. You have both voltage or both voltage sources connected, both inputs connected to your MOSFETs. Well, for problem 5, we just have VI connected to one MOSFET and the other is ground. And for diff pairs, you have two outputs, VO1, VO2. So how to solve, like what's the difference between diff pairs and the problem we just solved before? You can just refer to last week's discussion. So in last week, Kieran has solved diff pairs, and he has also gave many definitions of diff pairs. I like how to solve the differential mode gain. You can just refer to that, and you'll find the difference between our problem, homework problem, and diff pairs. What's the difference between them? Yeah, I'll just recommend you to look at his discussion slides in last week. That will be much helpful. And that's all I have for today. If you have questions, you can just ask. If not, thank you for your listening.